We have a complete map of the universe's history. We know how the first stars ignited after the Big Bang. We know how galaxies spiral and collide. We even know how stars die, exploding into supernovae or collapsing into black holes. But there is one chapter in this cosmic history book that has remained completely blank. It is arguably the most important chapter of all, our origin. For centuries, astronomers have been staring at a paradox. We can see giant molecular clouds where stars are about to be born, and we can see fully formed solar systems like our own. But the moment in between, the actual mechanism that turns dust into a planet, it has been invisible, a cosmic blackout. We have never actually seen a solar system in the process of being born. Everything we think we know about how Earth formed is based on forensic evidence, guessing what happened billions of years ago by looking at old rocks. We have been solving a crime without ever seeing the footage. Until now, deep. In the Orion Nebula, the James Webb Space Telescope has just captured a ghost. It is a baby star hidden inside a dark cocoon, and for the first time in human history, we aren't just guessing how planets form, we are watching it happen live. And what we are seeing is about to rewrite the textbook on how our own world came to be. To understand why this discovery is shaking the foundations of astrophysics, we have to look at how desperate we've been for answers. Living on a planet, you would assume we understand how it got here. We have walked on the moon, sent rovers to Mars, and cataloged over 6,000 exoplanets orbiting other stars. But the uncomfortable truth is that our understanding of planetary formation is largely theoretical. Our current standard model is built on extrapolation. It's like trying to reconstruct the construction of a skyscraper by looking at a pile of rubble and the finished building, but missing the entire construction phase. We analyze meteorites that crash into Earth, treating them like time capsules. We look at the cratered surfaces of Mercury or the gas bands of Jupiter and run computer simulations to reverse engineer their creation. These simulations tell a tidy story. They tell us that huge clouds of gas and dust collapse under gravity. They tell us that as the cloud collapses, it spins, flattening into a disk. They tell us that over millions of years, dust grains gently bump into each other, sticking together like dust bunnies under a bed, eventually growing into asteroids, and finally, planets. It's a great story. It makes sense mathematically. But there has always been a massive problem. We couldn't test it. The early stages of this process are shrouded in thick, opaque veils of gas. Visible light cannot penetrate these stellar nurseries. So for decades, the most critical moment in planetary evolution, the moment dust actually becomes rock, has been hidden from us. We needed a way to see through the curtain. The first crack in the mystery appeared thanks to the Herschel Space Telescope. Back in 2013, a team of astronomers launched the Herschel-Orion Protostar Survey, or HOPS. Their target was the Orion Molecular Cloud, the largest star factory in our galactic neighborhood. They weren't looking for fully formed stars. They were hunting for embryos. The survey was a massive success. They identified 15 new protostars, objects so young and deeply buried in cold gas that they had never been seen before. These weren't stars as we know them. They were barely warm, heating their surrounding gas to just 20 degrees above absolute zero. This was a crucial step. We finally had targets. But finding the stars was only half the battle. The bigger mystery remained. The planets. According to our simulations, the transition from dust to planet is a slow, grinding process. The nebular hypothesis suggests that after a star forms, a debris disk lingers for millions of years. In this calm, cooling disk, the planets slowly take shape. But when we looked at the universe, the timeline didn't add up. We've found gas giant planets orbiting stars that are only 2 million years old. In cosmic terms, that is the blink of an eye. If the standard model says it takes millions of years for a core to form, how do these planets exist so quickly? There was a missing mechanism, a turbocharger in the system that we weren't seeing. We needed to look at a system that wasn't millions of years old, but thousands. We needed to catch the process at the very beginning. Enter HOPS 315, located 1/300 light years away. This object is a stellar infant. It is less than 150,000 years old. In the life of a star, that is not even a toddler. It is a newborn. It has about 60% of the mass of our sun and is still frantically feeding, pulling in gas from the envelope around it. It is exactly the kind of chaotic, messy environment where planet formation shouldn't be happening yet, at least not according to the old theories. But when researchers pointed the James Webb Space Telescope At HOPS 315, they managed to peer through a gap in the surrounding clouds. Webb's infrared sensors didn't just take a picture, they broke down the light spectrum of the material swirling around the star. What they saw was shocking. The spectrum revealed the chemical fingerprints of two very specific things: warm silicon monoxide gas and tiny crystalline silicates. To a layperson, that sounds like chemistry jargon. To an astronomer, it is the smoking gun of creation. You see, as the gas around a star cools, elements solidify or condense in a very specific order. It's called the condensation sequence. Finding crystalline silicates means we are witnessing the exact moment gas is turning into solid rock. We aren't looking at a dust cloud anymore. We are looking at the first bricks of a future world being laid, and it is happening around a star that is only 150,000 years old. This shattered the timeline. We used to think planets formed in the quiet aftermath of star birth. HOPS 315 proves that planets start forming while the star is still being born. The oven is still preheating and the cake is already rising. This discovery was so significant that the team, led by Professors Melissa McClure and Meryl von Hoff, needed to confirm exactly where this was happening. James Webb is incredible at seeing hot inner regions of a star system, but to see the cooler outer shell, they needed a different set of eyes. They turned to ALMA, the Atacama Large Millimeter Array. This massive radio telescope network in Chile specializes in looking at cold dust. By overlaying the data from Webb and ALMA, they created a 3D map of this newborn system. Webb showed the hot, rocky chemistry happening close to the star, while ALMA mapped the cold molecular cloud further out. The data revealed something fascinating. The region where these silicate crystals are forming, where the first rocks are being born, is located at roughly the same distance from HOPS 315 as the asteroid belt is from our sun. This suggests that HOPS 315 isn't just a random anomaly. It is a mirror. We are likely looking at a near perfect replica of our own solar system 4.6 billion years ago. However, there was a twist in the data. When they analyzed the jets of gas shooting out of the star, they noticed something strange. The jets were suspiciously low in silicon. There was only about 2% of the expected amount. Where did the silicon go? Silicon is the primary ingredient for making rocks. If it wasn't in the gas jets, there was only one place it could be. It had already been locked away into solid objects. This was the final nail in the coffin for the slow formation theory. The missing silicon implies that large pebbles, planetesimals, have likely already formed. In less than 150,000 years, this system has gone from a cloud of gas to potentially housing kilometer-wide asteroids. The speed of creation is terrifyingly fast. So if we are watching a solar system in the first trimester of its life, can we predict what it will look like when it grows up? Because we now understand the condensation sequence, we can make an educated forecast. The destiny of this system is dictated by the snow line. Close to the star, it is too hot for ice to exist. Only tough materials with high melting points like iron, nickel, and those silicates we found can survive as solids. This is where the rocky planets will form. HOPS 315 is likely building its own versions of Mercury, Venus, Earth, and Mars right now. Further out, beyond the snow line, temperatures drop. Water, ammonia, and methane freeze into solid ice. This abundance of solid material allows planetary cores to grow massive quickly. They become so heavy that they start sucking in the surrounding gas, ballooning into gas giants. In our system, Jupiter and Saturn acted like bullies. They formed so fast and grew so large that their gravity disrupted the space between them and Mars. They prevented a planet from forming there, leaving behind a ring of failed rubble, our asteroid belt. Will HOPS 315 have an asteroid belt? It depends on whether it births a Jupiter. If a gas giant forms quickly enough to scatter the remaining planetesimals, then yes. If not, HOPS 315 might end up with a super Earth or an intermediate planet in that gap, something our solar system never produced. HOPS 315 has transformed from a faint dot in a telescope survey to the most important laboratory in astrophysics. It has bridged the gap between the models and reality. We now know that the universe wastes no time. The moment a star ignites, the clock starts ticking for the planets around it. The raw materials of life, the silicon in your bones, the iron in your blood, begin to forge together almost instantly in the chaotic heat of stellar birth. We are just starting to scratch the surface. Researchers are now scrambling to find more systems like HOPS 315 to see if this rapid formation is the rule or the exception. But one thing is certain: we are no longer just looking at the cosmos and wondering where we came from. We are finally watching the story of our origins unfold, one frame at a time. If you want to keep exploring the mysteries of the universe with us, make sure to subscribe and hit that notification bell. We've got deep dives coming up on the dark matter crisis and the search for life on Titan that you won't want to miss. Thanks for watching.